Hello everyone. Let's dive into the gears of neural networks, focusing on tensor operations. We'll explore their mathematical definitions and how they work geometrically. Understanding these is key to seeing how neural networks handle data and learn. We'll cover element-wise operations, broadcasting, the tensor dot product, reshaping tensors, and the geometric side of things. First up, tensors themselves. Think of them as multi-dimensional arrays. A single number is a zero-dimensional tensor, a list of numbers is a one-dimensional vector, and a table of numbers is a two-dimensional matrix. They're what deep learning frameworks use. Important terms here are rank or order, which is the number of dimensions, shape, which tells you the size of each dimension, and data type, like whether the numbers are integers or decimals. Now, element-wise operations, these are operations like addition, subtraction, multiplication, or applying a function like sine that happen on each individual element of one or more tensors. The tensors have to be the same shape for this to work. Mathematically, if you have two tensors A and B with the same shape, their element-wise sum C means each element in C is the sum of the corresponding elements in A and B. Here's a quick example using NumPy. We create two 2x2 arrays, A and B, and then perform element-wise addition and multiplication. You can see the results printed out. Next, broadcasting. This is a clever trick that allows libraries like NumPy to perform operations on arrays with different shapes. If the shapes are different, NumPy will stretch the smaller array to match the larger one, as long as the shapes are compatible based on a few rules. Essentially, it adds dimensions of size 1 to the left and then stretches dimensions of size 1 to match the other array's size. If sizes don't match and neither is 1, you get an error. For example, here we add a 2x2 array A to a 1D array B of shape 2. NumPy broadcasts B to match the shape of A before adding them. Then there's the tensor dot product. This is fundamental in linear algebra and neural networks. For two tensors, it involves summing up products of elements along specific axes. Matrix multiplication is a common form. If you have a matrix A of size m by n and a matrix B of size n by p, their product C is an m by p matrix. The element at row I, column j of C, is the sum of the products of elements from row I of A and column j of B. We show matrix multiplication with 2x2 matrices. We also do a tensor dot product with higher dimensions, a 3D tensor of shape 2 by 3 by 4, and a 2D tensor of shape 4 by 5. The resulting tensor has a shape of 2 by 3 by 5. We also have tensor reshaping. This is about changing the dimensions of a tensor without changing the actual numbers inside. It's really useful for getting tensors into the right format for certain operations. You can use methods like reshape, flatten, to turn a multi-dimensional array into a 1D array, squeeze to remove dimensions of size 1, expand dims to add dimensions of size 1, and transpose to swap axes. Here we take a 3 by 4 array A and reshape it into a 4 by 3 array B. We also show how to flatten A into a 1D array C. Let's look at the geometric side of these operations. Vectors can represent points or directions in space. Matrices can be seen as linear transformations, things like rotating, scaling, or shearing space. Element-wise operations are like applying independent transformations along each dimension. The dot product, particularly matrix multiplication, represents combining these linear transformations. Applying matrix B, then matrix A, is the same as applying the product of A and B. We illustrate this with an example of a rotation matrix applied to a vector, showing the original and rotated vectors on a plot. Finally, let's connect this to deep learning geometrically. Each layer in a neural network is essentially a series of tensor operations, matrix multiplications, additions, and nonlinear functions that geometrically transform the input data space. Training a neural network is about finding the right numbers, the weights and biases for these operations so that the network can transform the input data into a form that's easy to separate for classification or regression. Neural networks work in high-dimensional spaces, which can be hard to visualize, but the same geometric ideas from linear algebra still apply. So, in summary, we've covered the core tensor operations, element-wise, broadcasting, dot product, and reshaping. Understanding these operations and their geometric interpretations is key to grasping how neural networks learn by applying transformations to data in high-dimensional spaces. That wraps up our look at tensor operations.